Right. So in this topic, we're gonna talk about graphing in physics, and turns out that with your internal assessment and your labs and your practicals in this class, graphing is an absolutely critical thing to be able to know how to do. Now, if you had me in grade 10 last year, we did a bit of graphing. It's going to be a little more complicated in the IB, but you have a very good foundation from which to start. Okay, so the first thing we're going to do is I'm just going to kind of show you guys a few different types of graphs and the visual display of quantitative information, and we'll just kind of talk about sort of critically evaluate them and talk about try to get an idea of what kind of data they're trying to represent. Okay, so this ability to intelligently interpret visual data is absolutely critical, and so my question here is, can you do it? I know most of you can. All right, so if you take a look at this particular graph here, you have to also think about what is the difference between a graph and a chart. Is this a chart or a graph? Well, it depends kind of how you look at it. In some cases, it's very hard to really tell the difference. Okay, I'm calling this a graph of foreign footballers in Europe against the country. Now, remember that when you have a graph title, the first variable is the independent variable, and the second is the dependent. Okay, so really, you can think about it as this is kind of a graph that's skewed on the side. Now, it's not super scientific because country is not really a quantitative variable, right? So we have to be careful about what we graph in terms of our variables. We have to be able to quantify things. You can't really quantify a country. Now, we could talk about foreign footballers against population of country. That would be a way to quantify this graph. Okay. All right. How about this one? This is an interesting graph. All right. This is a graph of video game sales, violent crime against time. Okay, stuff to think about here, right? How about this one? You ever seen one of these happiness graphs? These are kind of funny. This is a graph of happiness against GDP per person. You know what is this? How do you quantify happiness, mean life satisfaction? Got to be careful about this. This is more of a chart than a graph. Okay. Now here's something that is quite scientific, and this is a graph. Pause the video and take a look and see if you can figure out what's being shown here. This is a graph of adjusted solar flux against time. All right. So what you can see here is you can clearly see cycles of solar flux, right, or the amount of radiation that's being in solar flux units that's being emitted by the sun. So this actually has something to do with sunspots, okay? So this is kind of an interesting thing. So the difference between this and one of those bar graphs previously is that this graph visually displays quantitatively two different variables that can be quantified or expressed with hard numbers, and that's what we do in this class. When we do experiments and measure things, we want to investigate how one variable affects another, the independent variables. So clearly the year is the dependent variable. The investigator chose to show data from certain years, and the flux units, the adjusted flux, is clearly the independent variable. Okay. How about this one? This is kind of interesting. Okay, this is a graph of latitude against month showing the midnight twilight and midnight sun. Okay, so you have different locations here. This is super cool. It's a really cool graph. You should pause and look at this graph a little more closely. Okay, how about this one? It's kind of a crazy design. It's the graph of local mean time against month showing astronomical twilight in sidereal time. It's very interesting. Okay, and here's one that looks pretty complicated. This was a messy graph, and sometimes even astrophysicists don't make graphs that are really kind of the graphs that we would want to make in IB physics. This is their title, Nebular Filter Transmission. Really what it is it's a graph of nebular filter transmission against wavelength. Okay, pretty interesting stuff. All right, now this is not a graph, clearly, but this is a visual display of qualitative information. This shows you the location of North American meteorite impact structures, so craters and things like that. Very interesting. Why is there an absence of craters or meteorite structures on the West Coast? Why are there so many in the Midwest and so few on the East Coast? That's a big question I'm going to ask you about in class, so we're going to talk about that. Okay? All right. Here's a very technical graph. All right. Clearly, this is a pie chart. It's not what's a chart. It's not a graph. So if you think about the experimental apparatus that you would use to create this graph, so clearly you would need a knife, you would need a fork, and you would need a human mouth or some mouth to consume the pie. So clearly the yellow part of the chart shows the pie that's not been eaten, not a graph. Okay? Here's one. I want you to pause the video and really look at this one. This graph clearly shows that there's been a growth in misleading charts over the years 2001 through 2004, right? Okay. All right. So anyway, let's talk about making graphs. All right. So I want you to pause the video and get out a sheet of graph paper. And I want you to graph this data on that graph paper. So take a few minutes to do it. I'm not going to I'm not going to tell you how to graph this. You should know how to graph data at this point. I'm not going to tell you how to do it. I just want to see how you do it, and then you can compare the graph you make to the way that I would graph it. Okay? Okay. So the question is, did you do it correctly? All right? So every graph has to have certain things. All right? Clearly, it has to have a title. Okay? Here's my S in meters, my distance, and my time in seconds right here. You know, how did I know that time was the independent variable? Well, you have a clue. You have a clue because the independent variable tends to, but not always, has an even interval between data points. Okay, distance here's my best fit line, which in this case is a curve. In this class, we refer to best fit lines to anything that best fits the data, which means that a curve can be referred to as a line in IB physics. Now, we would use the term linear fit if it's an actual line. All right, so that's something that you got to kind of get used to. And I have a definition of graph here: a visual representation of two or more things showing how they're related. It's the visual display of quantitative information. All right, and it allows us to recognize trends in the data. So clearly, if you look at these two variables, you can see that there's a positive correlation between them, even though it's not linear. As t increases, s also increases, though it's not linear, even though it goes through the origin. Okay, turns out this is a quadratic relationship between s and t. Okay, graphing is really, really important in this class. It is almost always the best way to present and analyze data. And in fact, in your labs, in your lab rubric, you will get points for your graphs. If you do not have a graph, you're going to lose a lot of points. Okay. Okay. This is from your homework study packet, and I'm asking you to suggest a relationship between y and x. So remember, from the mathematics you need for IB physics, one of the things you need to be able to do is look at functions and be able to get an idea of what function might be graphed algebraically. So go ahead and pause it. And in fact, you can get out your homework study packet and do this exercise with me as I guide you through it. But try it first. Okay? All right, so graph A is clearly linear. All right? And we say that it's proportional. The D and I are proportional to one another. And they're directly proportional because the y-intercept is 0, so it's straight in through the origin, and it can be. This would be modeled by this particular relationship, which you learned in algebra. Okay, graph B is not proportional, so be careful. Even though graph B is linear, it is not proportional. Okay, because B does not equal 0. It does not go through the origin. So you got to be really careful in IB. Differentiate between proportional and non-proportional. Just because something is linear does not mean that it's proportional in the way we think about it in the IB. Okay? All right. We would say that there's an inverse. Would we say this is an inverse relationship? We got to also be careful here because we say it's inversely related in terms of one thing going down as the other thing goes up. All right? But this is not an inverse relationship in the sense that y equals 1 over x, is it? So we have to also be very careful about that, okay? Because this can also be given as y equals mx plus b, where m is negative and b is also not equal to 0, okay? Now, here's a case where we have inversely proportional. So inversely proportional and inversely related are actually two different things, okay? So here is a graph in the form of y equals 1 over x, or c over x. Remember, these constants don't change the overall trend of the graph. They might, a constant, if you remember from your algebra, might stretch or compress a graph or whatever, but it's not going to change the actual shape of that function, okay, the overall shape. Okay. Here's some more graphs, E through H. Go ahead and pause and try these on your own first. All right. This is a pretty steep graph. This could be a quadratic. It could also be a cubic function because if it's a quadratic, it's going to continue over like this. If it's a cubic, it's going to go down like this. But since we're not dealing with a negative independent variable, we don't know actually what's happening on this side of the y-axis. So, and also because we're not given a scale, we don't know if it's cubic or if it's a squared function. It could even be something to the 4th power. We don't know that, okay? This one could be an exponential decrease, all right? It's probably not a quadratic because if it were a quadratic, we would be showing the rest of the graph coming out like this, right? And it's not, so it ends right there. So it could be something of that form where it's could be an exponential decrease. We don't really know, okay? Now this could be a square root. This is a classic square root function, right? Depending on the scale, y equals the square root of x tends to look like that. So this could be of that form, all right? And this looks like an exponential increase to me. Now, you might argue that this also could be a quadratic. I guess it could be. You don't really know, again, without having values, a scale on your d and I axes here, okay? All right. So a couple of guidelines for making graphs. I asked you to make that graph sort of cold before, and I didn't really tell you how to make it. I just wanted you. Now you can compare that graph that you made to see if it has all these bits and pieces on it. Number one, the independent variable is always on the x-axis. The dependent is always on the y. You know that, okay? Every graph should have a title, concise but descriptive, in the form of graph of dependent against independent, okay? The scale should suit the data ranges, right? You wouldn't have some crazy data range or scale where all your data is bunched up in one little tiny spot in the graph. You really want to use the space that you have, because remember what you're trying to do with the graph. You're trying to communicate quantitative information visually to the viewer. So if everything's all bunched up in a corner, that's really not a good way to show that, okay? The axes should be labeled with variable units and uncertainties. We'll talk about uncertainties in a little bit. You should use enough area. The data points should be clear. Error bars should be shown using a straight edge if you're doing it by hand. I will cover that in a bit. The line of best fit should be drawn. Could be a curve. Don't ever connect the data points dot to dot. You know that. You learned that a long time ago. For linear graphs, the lines of max and min slopes according to your uncertainty should be clearly shown. You don't know how to do that yet. I'm going to teach that to you. And you want to really think about whether the origin should be included in your graph, not just for linear graphs, but for also quadratic and other functions. And you think about what's the physical significance of that point. Often when you're doing a practical or a laboratory, you have to really think about whether it should go through the origin. And in some cases, if you make it go through the origin and it shouldn't, you might get points taken off, okay? All right, and I have here the independent variable is often evenly spaced because it's controlled by the experimenter, but not always. If you think about the lab that, for example, water against mass, right? The height of water against mass, your h variable, which was your independent variable that you controlled, you didn't have it evenly spaced, okay? So you got to be careful about it, but often it is going to be evenly spaced, okay? And here's an example of a proper graph. I think you've seen this graph before. Okay, this is graph, and don't worry about why I'm graphing t squared versus length, but t squared, here we go, t squared is the dependent variable, length is the independent variable, properly x and y. Here are my data points with my error bars. The error bars in x are quite small, but you can sort of see them, okay? In y, they're variable. I have the line of best fit, which is shown in black. The max is in red, and the min is in blue, okay? And this was made with a program called Logger Pro, which you guys will learn to use very soon, and you'll become very familiar with it.